Good morning, and I would like to also echo Jack's welcome and acknowledgement to the NIJ and to Debbie Figarelli and the NFSTC for putting on this workshop. So I'm lucky enough to give 3 talks in a row here, so I hope you don't get tired of me quickly. But I was asked to talk first about the current SWGDAM guidelines, and I'd like to give just a disclaimer that was not part of the SWGDAM committee. I don't speak on behalf of the SWGDAM group, and so the opinions are those of mine. So typically, there's a hierarchy of rules for forensic DNA labs, and we'll take a look at within the United States, the hierarchy that we use, and then as a comparison, the hierarchy of rules in Europe. So typically, in the U.S., we're all audited by the FBI, by the DNA Advisory Board, quality assurance standards, also INDIS procedures. In Europe, there's the European Network of Forensic Science Institute, and they develop their policies, much like the FBI's policies for auditing labs. And then for validation, we have your own laboratory protocols that you develop, your SOPs, based upon your validation studies. We also have SWGDAM guidelines, which are guidelines to help you in these validation procedures and so forth. The corollary in Europe would be recommendations from the ISFG, and so Jack mentioned the ISFG group, and I'll talk about them in just a few moments. The DNA Commission of the ISFG makes recommendations, and these can be adopted as national recommendations. So Austria would adopt the ISFG recommendations, and so would Germany, and so forth. And then in the lab, your individual analysts, the practice, their training, the case reports, all of this is based upon training and experience within the lab. So let's take then a brief review of the literature. Jack did a very good job setting us up to this point. And so we'll briefly go over the literature, and we'll start with this paper that Jack mentioned, the Peter Gill et al. Paper from the ISFG, the DNA Commission of the International Society of Forensic Genetics, Recommendations on the Interpretation of Mixtures. This is a 2006 paper. So I thought I would start off with the question of who is the ISFG and why do their recommendations matter? Well, the ISFG is an organization that was founded in 1968. It's an international organization, representation from all over the world. There are different working groups that make up the ISFG. So there's the English-speaking working group. There's the Spanish and Portuguese working group, the Italian working group. There's a Chinese working group now. And so the individual forensic genetic labs around the world have this international body in the ISFG that is there to help promote scientific knowledge and to help labs. And often there are DNA commissions that are developed to offer advice on recommendations for forensic genetic analysis. So starting back in 1989, DNA polymorphisms, PCR-based polymorphisms in 1992, and so forth. The ISFG has been very critical in the nomenclature of STR alleles, so the recommendations for how you name microvariants and so forth. This is all developed by the ISFG so that labs can have a way to communicate with one another. We're talking about 13 repeats in this lab and not looking at the repeat structure. You could potentially call it as 12 repeats in another lab. So there's recommendations on how we call these alleles that was developed by the ISFG. So in 2006, a committee was formed to discuss mixture interpretation. This included the executive committee of the ISFG. Niels Morling from Copenhagen is the president, current president. Peter Schneider was the past president. He's now the vice president. And Mickey Prinz from the New York OCME is the head of the working groups. Angel Caracero was previously a president of the ISFG. He's now, of course, the editor-in-chief of FSI Genetics. Also part of this ISFG article was Peter Gill and the mathematicians and statistician. As Jack said, we're very fortunate to have John Buckleton here. John was part of this group that wrote this paper. We also had Charles Brenner and Bruce Weir from the US that was part of this committee. So as Jack said, the paper is here. You can actually go to the ISFG website and you can download this paper, the commission. And as Jack noted, one point that was highlighted here is our discussions have highlighted a significant need for continuing education and research in this area. And the aim of this document was to, foremost, stimulate discussion, and also for other working groups, for other labs or countries to offer their recommendations. What do they think? Or what are they doing? So the aim of this was to invite proposals and criticisms in the form of comments and letters to the editor of the journal. As Jack mentioned, these are the recommendations. Of course, the likelihood ratio is the preferred method over random man not excluded. Scientists should be trained in using likelihood ratios and so forth. And we'll go through some of these specific recommendations later. But very important aspect here is, of course, number 4. That Clayton paper that Jack mentioned is a classic paper that is excellent for developing a framework on how to interpret mixtures. So in response to, in response to the ISFG paper, the UK came out. So Peter Gill, who was the author of the ISFG paper, was also the first author on the UK response. So the UK responded to the ISFG mostly very favorable. Yes, we agree with things, but there were slight things that they felt were a little different. And so they gave their response. The Germans came out with their response, first paper in 2006 by Peter Schneider that was in German, and then later this was published as an English version in IJLM. And then the European Network of Forensic Science Institutes came out with their statement, Niels Morling. The New Zealand and Australia groups came out with their support. And then the SWGDAM group, rather than coming out with a letter to the editor and stating we agree, we disagree, and so forth, decided to form a mixture interpretation subcommittee in January of 2007. We're fortunate to have 2 people on this mixture interpretation subcommittee. Todd Bill and Jack Ballantyne are here. These are the 15 members that were part of that SWGDAM mixture interpretation subcommittee. So feel free to, again, if you have any questions to Todd and Jack, they could offer some potential insight. But in 2010, in January, the SWGDAM committee approved the guidelines, and they are now published on the FBI website, on the CODIS website, CODIS group site here. So you can go to that link and get the guidelines. So a few things about the SWGDAM interpretation, STR interpretation guidelines. They're guidelines. They're not meant to be standards. So you should not be audited against this document. They're for autosomal STR typing, so there's no discussion about Y mixtures or MITO or CODIS databasing and so forth. So this is a document for forensic DNA testing labs because database labs may have different issues. So this is discussing predominantly for casework mixtures and not single source samples that would be put into a database. As Jack mentioned, the original STR interpretational guidelines in 2000 was a 4-page document that had 7 sentences that discussed mixtures. So it was a great need to update this document. So the first thing about the purpose and scope of the guidelines is to say that it supersedes the 2000 guidelines, and these are not intended to be applied retroactively. Guidance is provided for forensic casework, for applying thresholds, for detecting alleles, and for the appropriate statistical approaches. So these are the 3 main things that the guidelines discuss. The purpose and scope is to encourage labs to take a look at their SOPs and their validation data in light of these guidelines and to update these procedures as needed. And again, this document is discussing sort of the types of mixtures that you have with relatively high-quality DNA or at least alleles that are above stochastic threshold. This document is not intended to talk about the low template enhanced interrogation as John Butler describes it, where you're adding more cycles, more polymerase, you're increasing your injection times and so forth. These are recommendations are not to address that type of enhanced methods for improving or increasing the RFUs of profiles with low quantity and low or degraded samples. The purpose and scope, number 4, due to the types of the complexity of DNA typing results, it's impractical and infeasible to cover every aspect by a preset rule. So it's really important that you develop proper validation procedures and that your protocols can address this so that you can achieve greater consistency and accuracy among analysts within your laboratory. So the general flow here for the elements of DNA mixture interpretation is you have the principles, the theory, which can be the SWGDAM guidelines or the ISFG recommendations or other articles in the literature that you can use to sort of develop your principles, your theory. And then taking that, you develop your protocols through your validation studies to develop your own laboratory SOPs, and then that translates into practice through training and experience. So with the training within your laboratory. And of course, it's always critical, or at least it's important, to try to have consistency across analysts, and this will help by having periodic training. So again, it's welcome that the NIJ and the NFSTC is putting on this workshop, and of course it will be made available eventually online, but periodic training can help in this consistency across mixture DNA interpretation across your lab. So the overview of the guidelines. The first thing that the guidelines address is, can you identify a peak? Is it a peak? Is it an allele? Is the next step. Then it moves into the interpretation of the DNA typing results. So can you distinguish artifacts, developing peak height ratios, trying to identify the number of contributors to the profile, interpreting the interpretation of the results and the comparison of the results, and then addressing the statistical analysis of the results. One thing that you'll find as you read the guidelines is the word must versus should. So must is used 29 times in the document, and should is used 41 times. And so the way John explained this was that as they were writing the guidelines, if there was something that they felt was tied to the FBI quality assurance standards, then this became a must, since this is something that you would be doing anyway. So for example, the QAS standard 9.6.1, the laboratory shall identify controls, so forth. The SWGDAM interpretational guideline says you must establish criteria for evaluating controls. So where there's an item that is in the QAS document that you shall be doing, it became a must in the SWGDAM guidelines. But if it was just a recommendation, it was should. So you'll see that used, those two words used throughout the document. So the first step is to evaluate your data. So you should develop criteria to determine whether an instrumental response is detecting signal from an amplification product versus noise. And the first step that you would want to do then is to develop an analytical threshold. So the laboratory should establish an analytical threshold based upon signal to noise of your empirical data. Typically, you can have the signal to noise can be 3 times the standard deviation of the signal to noise. There are various methods to calculate or to develop an analytical threshold. I'll talk about that in the next lecture. The analytical threshold is supposed to define the minimum height requirement at and above which detected peaks can be reliably distinguished from background noise. Because this is based upon a distribution, occasionally you may see a peak that crosses the analytical threshold that is not, in fact, a peak. So it's important that you set that threshold properly. But again, because this is a distribution of noise values, it's possible that you can't encompass everything. So it should be sufficiently high enough to filter out the noise, but not so high that you're starting to filter out authentic peaks. So again, this is just looking at the highest peak here in this electropharogram. You can develop analytical thresholds based upon the different dye channels. The PET channel and the ABI kits typically have more noise associated with the red channels than, say, the blue channel. So you may do different analytical thresholds for different dye channels. So basically, your analytical threshold is dependent upon your instrument sensitivity. Basically, what is a peak? The next step is to determine if it's an allele. So there's a peak there. Does it mean it's an allele? So the second thing is to establish criteria to assign allele designations, and this can be done, with also by using off-ladder alleles and so forth. So developing guidelines for that and criteria for alleles that fall outside of the bins, so forth. So we'll go through step 3, which is looking at the different steps in going from, is it a peak, is it an allele, can we develop genotypes from this, and then using mixture ratios and peak height ratios to do deconvolution of a mixture. So the first step here in section 3 is non-allelic peaks. So peaks such as stutter, incomplete adenylation, spikes, so forth, can be introduced in the process. You could also have bleed through or pull up associated with over amplification. This is a slide that Johnny Seguela developed, looking at the sort of the noise here. You can see there's bleed through in the blue and the black channel here from the size standard. So you wouldn't want to develop your analytical threshold to, well, I want my threshold to be above these bleed through peaks, because then you're artificially setting it high. So you need to consider that as you do your validation studies. This is from a negative. You also have to consider dye artifacts, dye blobs, understand where they're occurring with your kit. And again, making sure that, well, I know there's a dye blob here, and the blue channel at about 220, so I'm going to set my analytical threshold up here, so that way I won't have to worry about that dye blob anymore. So you shouldn't set your threshold based upon these dye blobs, because they typically, dye blobs will occur as the kit gets older and so forth, as the dyes dissociate from the primers. And so with new kits, you may not see a dye blob for a while. So the threshold is applied to let you know that perhaps not all of the information has been developed or detected. So this threshold is called the stochastic threshold. This is the value in which it's reasonable to assume that dropout has not occurred within a single source sample. So the analytical threshold is based upon the noise of the instrument. So this is an instrumental issue. So you're wanting to determine whether the noise of the instrument, at the level of which the noise is there, and you're able to see if a peak is authentic or not. The stochastic threshold is developed so that you can determine whether or not the peak may be homozygous or a heterozygote, where you may have dropout. So this can be dependent upon the type of kit that you use and the detection instrument that you use. This is just sort of hypothetical examples. This is from a paper from Peter Gill. So you have in sample 1, the 2 peaks are heterozygote, and they're above this T or dropout threshold that Peter uses here. Here's an example where you have a peak that's just below your dropout threshold, and there's one peak there. So the question is this a homozygous peak that's fully represented here in this sample, or is this a heterozygous situation where the other allele has dropped out? And John Buckleton will talk about this later, that you can develop probabilities. In this case, there's a very low probability here, since you're so close to this detection dropout threshold, that this is most likely a homozygous peak. But if you have, let's just say this B was not here. If you had this A, then you would be below your stochastic threshold, and so the probability that there's a loss of a sister allele is much higher in that case. So here in this case, we actually have 2 peaks represented. They're both below threshold, stochastic threshold or the dropout threshold, but they're above the analytical threshold. So are they peaks? Yes. Is this a heterozygote? You could say yes if this is a single source sample. Even though they're both below the stochastic threshold, you do see 2 peaks, and if you have a single source sample, that's what you would expect. It's reasonable to assume. So the way that you assess your stochastic threshold is to look across, do multiple loci in a dilution series, and you look for the RFU value at which it's reasonable to assume that at a given locus, dropout has not occurred. So this is sort of a summary here. At, let's say, 50 RFUs, we have our analytical threshold, and this has been called several things. Bruce Vidali calls it the PAT in his paper. It's been called the reporting threshold, the noise threshold, the limit of detection. So for nomenclature purposes, we'll call it analytical threshold. Below this threshold, you have noise, and if there's a peak there, it's not considered reliable. And so you can think of the analytical threshold as the floor, and you can't look through the floor unless you're Superman with X-ray vision, which we're not. So any peaks below the analytical threshold you would not consider reliable. At 150 RFUs, we have the stochastic threshold, or the dropout threshold that may be also used. Again, Bruce Vidali calls this the MIT, so we'll call it the stochastic. if a peak crosses this stochastic threshold, then your confidence that this is, in fact, if it's a single peak, that it's a homozygous individual is quite high. Now, peaks that fall between the analytical threshold and the stochastic threshold are real, but it's uncertain as to whether this single peak is a homozygous or a heterozygote with a sister allele that's lost. And so there's special considerations that one should take, especially in the types of statistical analysis. So for exclusionary statistics like CPE, this would be an authentic peak. However, it could not be used in a statistical evaluation of the data, which we'll talk about more later. So the two thresholds, the analytical threshold, which is based upon the instrument sensitivity, is it a peak, versus the stochastic or dropout threshold, in which you're looking at the biological sensitivity of your kit. And so typically, these values can be 150 to 200 RFUs, and this is also impacted by, again, the type of kit that you're using, or the injection parameters and so forth. So once we've established if it's a peak, and then we've established is it an allele, we can move on to determine peak height ratios. So amplification of low-level DNA, this is, again, we're talking about relatively high quality or high level DNA samples, at least, half to 1 nanogram plus. Your two alleles can be confident that you have consistent peak heights. So if you're talking about amplifying DNA at very low levels, say 100 picograms or less, your peak height ratios may be highly variable. So this is what this section here is discussing. If you're using extra cycles, extra TAC, increased injections, and these sort of enhanced methods, your peak height ratios can be very different than what you would have at, say, 1 nanogram. So I'll talk about this later in the enhancement lecture after lunch. So peak height ratios, we're looking at, of course, you calculate these by dividing the low or the small allele by the high allele multiplied by 100. So typically with high quality 1 nanogram or so data, 1 nanogram input DNA, you can typically have peak height ratios above 60% or so. So the guidelines, the laboratory should establish peak height ratio requirements based upon your data from single source samples. You could have different peak height ratios for different loci. So for your FGA, where you may have a wide range or a wide spread between the two alleles, you may see some variation in your peak height ratios. My colleague Dave Dewar at NIST has developed a software program that we're in the process of writing up the protocol here, at least how to use the software, and eventually we'll put this on Starbase. But he's developed this program that you can take your data from from your validation study, and you can just simply drop it into this Excel spreadsheet, and it will spit out for you all of the peak height ratio values, and it will also break it down. So this is one repeat difference, so one repeat less here at VWA. You can see that the average peak height was 90%. If you have two repeats that are two alleles that are different by two repeats, your peak height ratio is at 89% and so forth. So overall, even if you have 5 repeats between the two alleles, you have pretty good peak height ratio values here. So again, you can establish peak height differences depending upon the locus. You can also use dilution series. You can also see that at different dilution series, once you go from 1 nanogram down to, say, 10 picograms, you'll start to see the peak height ratios will become highly variable. So this is some data that Becky Hill in my group at NIST developed on. This is a little bit different than what you would do for your typical validation, because this was a study that she was doing with low copy, low template DNA testing. So this is where she added extra cycles. So this was 31 PCR cycles, and you can see at 100 picograms, the peak height ratio average was 69%, but it's highly variable because you're down here at the stochastic range here of 100 picograms. So you can get a situation where the peak height ratio is less than 0.5. And then as you go down to 50 picograms, you can start to see severe imbalance. So 26%, 29%, then you can have one that's 90%. And then when you get down to 10 picograms, you can get the ultimate peak height ratio difference, in which you have dropout, where you don't detect the sister allele. So in that case, your peak height ratio is 0. So you can see that the average is much different. So as you start to go down in your dilution series, you can start to see variations in your peak height ratios. So Todd Beal will talk about this in his talk. This is what Todd has at the ATF lab. They've developed a minimum peak height ratio where they take the average peak height ratio minus 3 standard deviations, 3 times the standard deviation. And it's quite intuitive, as you would expect. When you're up here in the high RFUs, your peak height ratios are pretty normal, but then as you start to go down, you can start to see that the peak height ratio can be highly variable. So Todd will talk more about this later. It's typically with artifacts with non-allelic peaks, such as stutter, these need to be characterized too. So generally when you're talking about stutter and non-template addition, these can be characterized based upon the size of the peak. So we can take the stutter percentage as the height of the stutter allele divided by the height of the true allele, and you can come up with your stutter percentage. Again, Dave Dewar has developed another Excel-based software in which you can it'll take the data and it will calculate the stutter percentages for you. Of course, I think it's most people just simply use the applied biosystems or Promega values that are plugged into GMapper or whatever program that you're using as defaults. But you can develop your own stutter thresholds. And the stutter thresholds can vary. So this is TPOX, which is a AATG repeat, and you can see that the stutter percentages are quite low. So here for the 8 allele, your median stutter percentage is 2%. So this is a very nice marker where you have very low stutter, very low mutation rate, but not so great for mixture interpretation. This program will plot that. So here you have TPOX. You can see as the allele size increases, the stutter percentage also increases. If you take a look at D21, which is a complex repeat, you can see that the stutter increases here, 27 allele, 6%, 7%, 8%, 9%. Then when you get a microvariant like 30.2 that breaks up the repeat, you can get the stutter percentage to drop, and then it starts back again with 31 and so forth. So you can actually visualize this. So here we have the repeat. As the repeat size increases, the number of repeats increase, your stutter percentage increases. Here's a microvariant. Interestingly, at the 31.2, there's a wide spread between the stutter percentage here. So there seems to be a lot of variability that you can get also in these microvariants too. So the reason that stutter should be considered during mixture interpretation in the guidelines, this is addressed in section 3.5.8. When you have a minor contributor and there's a peak and a stutter position, you can have three potential scenarios. That stutter peak is stutter. It could be an allele, or it could be indistinguishable as either stutter or an allele. And so in the ISFG guidelines, this is section 6 of the ISFG guidelines, this is addressed in the point that if you have this situation here, where you have a major contributor, alleles C and D, and at allele A, you have a minor contributor. This peak here at B could be stutter from the C allele, or it could be the sister allele of A. Say the minor contributor is a heterozygote, AB. And so the ISFG recommendation said that if you have this situation where a stutter peak is indistinguishable from a minor allele, from a minor contributor, then you should consider that as part of your statistical calculation. So if you were doing a probability of inclusion, you would combine the frequencies of A and B and C and D. So generally, this is just going through, I just mentioned this. If you're looking at the height of the stutter peak, it exceeds your stutter expectation, then it's probably an allele. So if the stutter peak is really high, over your stutter percentage, then you should consider that as an allele. If it's at or below your stutter percentage, then it's generally designated as a stutter peak. However, it could be possible that it is an allelic peak. And so here's another example. Jack mentioned Bruce Heidelbrecht. This is an example that Bruce gave me where we have here, the 9 and 11. So we're looking at peak heights of 215 and 285. Well, here's the stutter peak at 221. And so if you're using exclusionary statistics, then since the stutter peak is basically the same height as your other two minor peaks, and you're not making you're not coming up with you're not making any types of assumptions as to the number of contributors here, then it should be considered then that the stutter peak should be considered in your stats. This is, again, from the ISFG paper. So this is, again, in Peter Schneider, once again, if there's a suspicious peak, you should consider it as part of the interpretation. Okay, so we've developed thresholds. Analytical threshold for the noise of the instrument, your peak height ratio for determining whether it's an allele or not, for your heterozygote peak balance, and then your stutter percentage or your stutter threshold for determining if a peak is stutter or if it should be considered as a true allele. So the section 3, continuing on, we've looked at peak height ratio. We're now going to consider 3.4, the number of contributors to the profile. So typically, if you observe 3 or more alleles at 1 or more loci, or the peak height ratios are much different than what you expect, then you could consider that there are, this is a mixture, then you can determine the number of contributors. So you should establish guidelines for determining the minimum number of contributors. This was a presentation at a Promega meeting several years ago from a group in Tennessee, at University of Tennessee. They found that in their study looking at multiple individuals, for single source samples, 99% of the Caucasian population had 20 to 26 alleles. Typically, if you see an average of 23 bands or 23 alleles, peaks, you have a single source sample. But this is just looking at the 13 CODIS loci. If you count the number of alleles and you find somewhere between 30 and 45, then you probably have a two-person mixture. And for three-person mixtures, they found between 39 and 57. So there's the potential for overlap here, but this is just one way to determine the number of contributors is to simply see how many alleles are present. This is a paper from Dan Crane where he, in his paper, estimated that about 3% to 4% of three-person mixtures would present as 4 or fewer loci. John Buckleton published a paper. This is a very nice paper, sort of in response to that, understanding the uncertainty and the number of contributors. One thing that you can also do, I like this particular table because it shows the value of certain loci for determining the number of alleles. So this is the probability. This is SGM plus the probability in a two-person mixture that you would see only one peak at D3 is about 1%, and so the probability you would see two peaks with two people at D3 is 24% and so forth. So some markers, such as D16, are not that great when you're looking at finding 4 different alleles at D16, only about 16% of the time. But other markers like D18, about 43% of the time you would see 4 peaks. And so the probability that you would only see 3 alleles, this is just in SGM plus, and we're not looking at TPOX here in SGM plus, but that would fall below here, D16. Section 3.4, composite profiles. So you should establish guidelines for generating composite results. Typically, if you have separate extracts from different locations are combined, this is not considered a composite profile. Mixture ratios. So we've developed peak height ratios that most likely explain the combination of alleles. So in this case here with THO1, we have 4 alleles. You can develop the peak height ratios between A and B. So this is 46%, C and D, 44%. So the most likely combination that makes the most sense here is A and C, which has an 81% peak height ratio as the major contributor, and B and D, which has a 77% peak height ratio for your minor contributor. So using that peak height ratio information to develop the different genotypes or the different allele combinations. You can also use the mixture ratio here to determine the contribution of the major to the minor. So in this case, you would sum up all of the peak heights for all 4 alleles, and you would divide the A plus C for the major component, so you would get 68% of the contribution is from the major and 31% from the minor. So this is about a 2-to-1 mixture ratio here. So that mixed ratio can be important for your deconvolution, which Chris McGuire will talk about later. So you can also classify the types of mixtures that you encounter, because the type of mixture that you encounter can also be useful in determining the type of statistic that you will be doing later. So this is based upon the German Stain Commission, Peter Schneider's paper in 2006 and 2009, where they determined that there are basically 3 types of mixtures. Type A mixture, in which There's almost an equal contribution between the two individuals. There's no clear major or minor, but all of the alleles are above stochastic thresholds, so there's no issue with stochastic effects with having alleles that are below your stochastic threshold. A type B mixture is one in which you have a clear distinction between the major and the minor, and typically the peak-height ratios are about 4:1 for optimal deconvolution, and there's no evidence of stochastic effect. So the minor alleles are all above stochastic threshold, and there's this clear distinction between major and minor. And then you have the type C mixtures, which are mixtures in which there's no real major contributor you can identify. The peaks all look about the same. There's no clear distinction, and you have some alleles that are below stochastic threshold. So these are type C mixtures. And not every single mixture will fall into one of these three categories. You may have a mixture that looks like a type A, but because of DNA degradation, it may also look like a type C with some of the larger alleles. So you could have sort of this combination of the two. So the SWGDAM guidelines, the way that the nomenclature works here, if it's a type A mixture, this is called indistinguishable, where you cannot determine the major and minor. If it's a type B mixture, it's called distinguishable in the guidelines, and if it's a type C mixture, it's called uninterpretable. Evidence taken from an intimate sample, of course, this is as determined by the laboratory. What's an intimate sample? Are expected to yield DNA from an individual from whom the sample was taken. So you should establish guidelines. So I'll go through these, through this quick example. Again, this was an example that was provided by Bruce Heidelbrecht from the Maryland State Police. So based upon the mix ratio, based upon the entire profile, is about 0.6 victim to 1 unknown. There's no stochastic issues associated with this loci, and the stochastic threshold is at 150. So if we know that this is an intimate sample, we can determine that the victim's alleles are 13 and 17, so that leaves the 15 allele as belonging to an unknown individual. So the question is it possible that the donor of this 15 allele, is it a 15 with a dropout? So the Brits, the FSS, use the F designation. We also may use the X designation here. So is it a 15 with a dropout, or is it a homozygous 15, or is it a heterozygote with allele sharing either with the 13 allele or the 17 allele? So you can go through and look at, based upon your peak height ratio data, and this mixture ratio can be used for deconvolution. Chris McGuire, again, will talk more about this. But if we consider that there's dropout, then that means the 13, 17 from the victim would have a peak height ratio of 77%, which is quite reasonable. But since this allele at 15 is at 453 RFUs, it would be unreasonable to assume that dropout has occurred. So that would not be a possibility here, that dropout has occurred. If the donor was a 15, 17, well, that means the 17 allele gets split. So some of that 17 allele belongs to the victim, some of that 17 allele belongs to this donor. And if you do the peak height ratio, you would see that the victim peak height ratio would drop from 77% down to 31%, and the peak height ratio between the 15 and the 17 would be 26%. If the donor was a 13-15, again, we're going to split that 13 allele, and so the peak height ratio of the victim is 52%. The peak height ratio of the donor would be 33%, so this is unlikely. So the most likely scenario here is that the donor is a 15-15 homozygote. So this is a case where you can use your peak height ratio and your mix ratio and doing the various possibilities of mixture deconvolution. So I'm going to finish up with a couple of other slight scenarios. Again, section 3.5, it's also important to consider that degradation may have occurred in your profile. This is an example that Steve Myers from California DOJ, where you have here in the lower molecular weight marker, it looks like a type A, where there's equal contribution of all alleles. And then you look over here at the higher molecular weight marker, and you're seeing what looks like a 5-to-1 ratio. So your ratio changed from being 1-to-1 to 5-to-1. So it's an indication that degradation has occurred. So you have to consider that. That may make an impact across your profile. So once you are finished with your determination of alleles and developing genotypes, deconvolution, you have to make a conclusion where the known individual cannot be excluded, or the individual is excluded. The results are uninterpretable, and so you have to establish guidelines. So the laboratory must establish guidelines to ensure that the results come from the evidence before comparison to any known sample, other than those of an assumed contributor, such as the vaginal swab. You can assume that the victim is part of that profile. So this was an important issue that the SWGDAM committee felt that this should be a must. So the laboratory must establish guidelines to ensure that the typing results from the evidence is interpreted before comparison to the known samples. Buckleton and Jim Curran published this paper in 2008. This is I think it's already a classic paper, and one that should be part of your literature reading for new analysts. In this paper, a discussion of the merits of the random man not excluded and likelihood ratios. Again, we're fortunate to have him here, and he'll talk on this subject tomorrow. But in that paper, this quote, there's a considerable aura of DNA evidence, and because of this aura, it's vital that weak evidence is correctly represented as being weak or not presented at all. So this is the reason why, if you're going to include someone in support of any conclusion, section 4.1, you should perform a statistical analysis. So you can calculate the CPE or random match probability or likelihood ratio, but it should be on the evidence and not from the known sample. You should not use inconclusive or uninterpretable data in this statistical analysis. There's a brief section, 4.6, on the statistical analysis. I won't go through any of this because we'll have Todd Beal will talk about this later today. Basically, just here's a table, the only table from the guidelines that shows situations in which you could use random match probability or exclusionary statistics or the likelihood ratio. Again, you have to document the formula that you use and the types of statistical analysis that you do. And again, this is section 4.6.3. CPE, CPI alleles below the stochastic threshold may not be used to support an inclusion. So if you have a type A or a type B mixture, indistinguishable or distinguishable, you should perform a statistical analysis, but type C, uninterpretable, a statistical analysis should not be performed. And again, we'll get lots of details on this, so I won't talk about the different types of stats. So to summarize, the new guidelines are meant to provide guidance for casework analyses to identify and apply thresholds. That's the first big part of the guidelines, for determining alleles and interpretation, and then determine the appropriate statistical approaches for interpreting autosomal STRs. Again, it's hoped that labs will be encouraged to review their SOPs and their validation data in light of these guidelines and update their procedures as necessary. Thank you very much. I don't know if we have time for questions, but we also, I think the other speakers will agree that if you have questions but you're maybe a little shy about getting up and asking, if you want to write it down on a piece of paper or something and hand it, put it up here later, we'll try to, perhaps at the end of the day, we'll type them up and try to address them if you're a little shy about getting up. So, thank you.